Hello to all of you, this is Dr. Dhaval Maheta, and today we are going to discuss about non-parametric statistics in R. In our previous video, we have talked about what is a parametric test. Basically, all t-test, z-test and ANOVA falls in the category of parametric test. But there is a basic assumption for using this test, and that assumption is the assumption of normality and assumption of equal variances. It means that if your data is normally distributed and if the variances between the two groups or more than two groups are equal, then only we can deploy parametric test. But in the real life data, it is very difficult to get the data which is normally distributed or the groups which have equal variances. So in such scenario, we are using the non-parametric version of the parametric test. So for each parametric test, we are having its non-parametric equivalence. So what is the difference between this, both of them? Let's try to understand. In case of parametric test, the distribution assumption, what we are assuming is normal. In non-parametric, we can work on any distribution. Assume variances, that is between the two groups, there should be the homogeneity which should be there. In case of non-parametric, even if the homogeneity is not there, we can go ahead. Typical data which is required in parametric is ratio or interval, while in case of non-parametric, you can also work on ordinal or nominal data. Data set relationships, it should be independent. Here it can be any relationships. Normally, parametric test runs on the comparison of the means of two groups or the sample mean compared with the population mean. In case of non-parametric, the test runs on the comparison of medians, and that's the reason the non-parametric tests are less affected by the outliers because we are considering median here. In case of parametric, we can draw more conclusions as we are using mean. Reliability of this test, parametric test, is very high because we are considering all the observations which are there in the data. While in case of non-parametric, the reliability of the test is average. If we talk about hypothesis, in case of parametric, it is rigidly framed, while in case of non-parametric, it is loosely framed. Choosing the parametric and non-parametric test, if you are carrying out the correlation test and if your data is normally distributed and if dependent and independent variables are in ratio, then we are using Pearson. While if it is in nominal and ordinal, we are using the Spearman. If we are comparing two groups, then here in case of parametric, we are running independent measures t-test, while in case of non-parametric, we are running mann, whitney, u-test. If there are more than two groups, then in parametric, we are running one-day independent measures, that is ANOVA. Same for non-parametric, we are having a kruskalwallis test. Repeated measures two condition, that is a dependent sample t-test, paired sample t-test. Here we are using it in parametric test. The non-parametric equivalence of this is a wilcoxon test. If we talk about repeated measures, more than two conditions, that means that the observations are taken at more than two time intervals. So here we are using repeated measures ANOVA, here we are using Friedman test. Now let us understand how we will carry out all this test in R. Okay, how many types of tests are there? Basically, three types of tests are there. Test of difference between groups, that is we are considering the independent sample. Test of difference between the variables, it is a dependent sample paired, that is before and after. And test of relationship between the samples. Okay, let's go in the R script and try to understand. Now there is one data which is trees. When I will run it, you will be able to see that what are the variables in it. So we are having girth, height and volume. So height we are having of all the trees, there are 31 trees are there. Now I want to check that is this height which is there of the data frame, is it significantly different? Is it significantly different from the median, that is a population median, that is 70. So I am saying median is equal to 70 and the alternative is median is greater than 70. So I will attach this and I will run wilcox.test height. Alternative is greater than, mu is 70, right? And the confidence interval is true. I will run this test. So here I'll get the p-value which is less than 0.05 and therefore we reject the null hypothesis, which means that there is a significant difference in the data frame median and the population median, or the median which has been, you can say, the median which is given, right, or the claim which is there. Now we want to compare the median of two groups, right? And again I will run the data frame, that is empty cars data frame. I will run it, and let us try to understand this data frame. Here we are having 32 different cars and the mileage is given. I want to see that is the mileage of the vehicle different in automatic and manual car or not. So my null hypothesis is there is no significant difference in the mileage of the cars according to the automatic and manual transmission. The alternative is there is a significant difference where eta is a population median. So when I want to carry out this analysis, first thing I should do is I will have to convert the this AM variable into the factor variable. So I'm making this as fam factor EM labels automatic and manual. When I'll run it, and I'll use wilcox.test mpg tilde fam alternative two-sided and run. And what is the answer which I get? The answer is this p-value is less than 0.05, and therefore we reject the null hypothesis that there is no significant difference in the mileage of the vehicle according to the automatic or manual transmission. As the p-value is very less than 0.05, we reject null. It means that the difference is large. Now how much is the difference? So we say t apply mpg fam comma mean. Yes, you are right, we are computing mean here, right? Because t apply is not the part of wilcoxon test, just we are comparing the mean of it, that how much is the difference is there. So don't get confused, t test is not this t apply is not the part of wilcoxon test, and that's the reason we can use mean here. Fine. Now let's go ahead and try to understand the dependent sample t-test. So the non-parametric equivalent of dependent sample t-test is paired wilcoxon test. So what is my null hypothesis? There is no significant difference in the median before and after the treatment, and here the significant difference is there. First of all, let me populate the data, run. So how much extra hours of sleep a person gets? There are two groups, 1 and 2. When I'll run it, I'll get all the variables on right hand side. Group factor, that is how much extra sleep is there. Group factor drug given or not given. Now I'll activate the file, that is a sleep. It's a default data frame which is given in the R. When I'll activate attach sleep, I can run this wilcoxon test, that is considered to be the non-parametric equivalent of dependent sample t-test. This mann whitney is non-parametric equivalent of independent sample t-test, and this is dependent sample t-test, right? Non-parametric equivalent, before and after. So I want to compare that what is the difference in the sleep before and after the treatment. So I can write this command in two ways: wilcox.test extra sleep tilde group sleep paired true. This is one. Another method is wilcox.test extra for group 1 comma group 2. In both the case your results will be same. You can see here you are getting the result 0.00901, and here you will also get the same result 0.00901. So here, as the p-value is less than 0.05, we reject the null hypothesis. We will say that there is a significant difference in two groups. When we'll plot this, so extra sleep, that is group 2 are getting extra sleep when they are taking some drug in comparison to group 1, right? So group 1 may be a placebo effect, and group 2 may be because they are inducing some drug, right? So here we are comparing the same you can say same respondents before and after. Now when we are having more than two groups, normally we are using ANOVA, but when we are not able to establish the normality in the data, we will have to go for the non-parametric version of ANOVA, and for that we are using the kruskalwallis test. First of all, let us see the data frame orange. I want to see the circumference which is there, right? I want to compare the circumference of 5 types of tree, 1, 2, 3, 4, 5, and is the circumference different in 5 types of trees or not. So first of all, I'll attach orange, and the command line will be kruskal.test circumference comma tree. Data set is orange. Our null hypothesis is there is no significant difference. I can just write it down here. There is no significant difference in the median, okay, of these 5 trees. Alternative is there is significant difference in the median of these 5 trees. When I'll run this, I'll get Kruskal test as the p-value is 0.4401. So here we fail to reject null hypothesis, or in layman language, you cannot write such thing in papers that we accept null hypothesis, but for your understanding, we can say that there is no significant difference in the circumference of the tree according to the type of the tree. It is more or less same. We can also confirm this thing by running the Tucky's test, fit Tucky, and you can see neither of the pair, when one first tree median compared with third, 5 compared with 3, 2 compared with 3, 4 compared with 3, neither of them are having p-value less than 0.05. The desirable thing is that the p-value should be less than 0.05, then we can say that this difference is large. Here the difference is not so large, and therefore more or less circumference of all the trees are same. This we can further confirm by using the circumference tilde, and I'll use trees. You can see more or less the medians are equal. We can also plot the fit, where those pairs, this we have previously discussed also, those pairs which are not dissected by 0. So 1 and 3 when 1 and 3, this is a confidence interval of 1 and 3. As it is dissected by 0, we can say that the difference is not so large. I want the pair, I'm looking for the pair whose confidence interval is not dissected by 0, then we can say that difference is very, very large. Now we are having a dependent sample t-test, and then we are having repeated measures ANOVA when the observations are taken at more than 2 time intervals. Similarly, here also we are having the non-parametric equivalent of this, and that is Friedman test. When I'll run this test, my null hypothesis is there is no significant difference. So I have created this data frame. Blood pressure is this. You can create this data frame in your scripts also. My null hypothesis is all treatments are equal, and the alternative is at least one treatment is different. Then the blood pressure is created, the data frame is created, and then we will carry out the Friedman test. Now we will formally run the Friedman test. First of all, we will attach the blood pressure to make the command line simple. The null hypothesis is there is no significant difference in the blood pressure according to the treatment, keeping patient as a blocking factor. I'll get the answer, that is a p-value is more than 0.05, therefore we fail to reject null. It means that there is no significant effect of the treatment. This treatment, 3 types of treatments are there. There is no significant effect of treatment on the blood pressure when we are blocking the patient. This is a Friedman test. Now there can be a possibility that both of your variables are in categorical scale, like on one side it is urban and rural, and on other side it is literate, illiterate, or you are having on one side bias and non-bias, and on another you are having male and female. So in such cases, when both of them are running in category, you are using the chi-square analysis. And here the words which we will be using are there is no significant association. First of all, we will have to see the data file. This data file is already available in the default data frame of R. The name of the data file is ESOPH, that is esophagus cancer, or a esophagus. Now what they have collected the data according to the age group, alcohol consumption, tobacco consumption, number of cases, and controls. So when I'll just write down health ESOPH, I'll be able to get the details of the entire data frame. So the age group is there, the alcohol consumption is there, the tobacco consumption is there, and the number of cases are there, and number of controls. So how many number of cases are there for esophagus cancer? So first of all, I am running the tabulation part. X tabs tell me the number of cases tilde according to the alcohol consumption. So I will attach, I'll run it, and I'll get alcohol consumption. Right now, tell me the controls, that is those who are consuming the alcohol and still they don't have anything. So run. So there are 29 such cases which were consuming the alcohol and maybe having a esophagus cancer. Okay, so 0 to 39 gram per day, 29 cases are there. 40 to 79, 75 cases are there. So this is a consumption which is there of alcohol. This is though they are consuming, they were not having the cancer. This is a control group, and this is the group in which the cases were recorded. Now what I'll have to do, I'll have to find out is there any association between the alcohol consumption and the cases or not. So first of all, I'll have to bind this alcohol 1 with alcohol 2. I will have to create the structure. So for that purpose, what I'll do is I'll go here, C bind alcohol X tabs, C bind n cases, this one, n cases, and controls tilde alcohol consumption usov. So what will happen when I'll run this command? Both alcohol 1 and alcohol 2 will get combined. You can see here. Now the data which was like in this row format has taken the format of columns. Right. Just I have to simply write down summary and alcohol. But first of all, we will have to see the null hypothesis. The null hypothesis is there is no significant association between alcohol consumption and esophageal cancer. Yeah. And here there is a significant association between them. So when I'll run the summary, what I'll get is a p-value. If you see the p-value, it's less than 0.05, and therefore we can say that we reject null hypothesis. Which means that there is a strong association between the alcohol consumption and esophagus cancer. When I plot it on right hand side, you can see the mosaic plot. So number of cases where are more when you are consuming more than when you are consuming 40 to 79, the number of cases are 75. Now the interesting part is when the alcohol consumption increases, the number of cases decreases. Now that's something weird result which is there. But anyway, this is a data set and we have to work on it, right? Now in control group also we can see some pattern here. Now we want to carry out the chi-square with another data frame, and for that I'll be using the empty cars data set, run. And I want to generate the result between vertical and straight engine and automatic and manual car. So I'll say T is equal to table VSAM T. So there are 12 cars which are 0, that is 0 in the sense 0 is automatic, and VS. Now let us check what is coded as VNS in empty cars. So I'll get the result on right hand side. So V shift is coded as 0 and 1 is coded as straight. So V shift engine and automatic car, there are automatic 12 cars are such. Okay. Straight engine and manual, there are 7 such cars. So we can generate this tabular form. Now I want to run the analysis between these two. What will be a null? Null hypothesis is there is no significant association between the engine type and the transmission. Here there is a significant association between engine type and transmission. I'll run the chi-square test, chi-square dot test. I got the p-value. Here the p-value is more than 0.05, therefore we fail to reject null hypothesis. It means that there is no association between vertical and straight engine on automatic or manual, right? Then I'll use chi-square. I can create this I can create this as a variable, and then I'll write chi-expected. Now what do I mean by this? Normally you can carry out chi-square when the expected frequency in all the cells is more than 5. In any of the cell, if the expected frequency. I'm not talking about observed frequency, which is the real raw data. I'm talking about expected frequency. When it goes down below 5, we are not in the position to use chi-square. Instead of this, we will be using Fisher's exact test. Okay, then there is a library G models. I can activate the library and I can get the output in much more organized format. I'll just write on cross tabulation AM vs chi-square true, and you can see how much organized it gives me, right? What are the cell contains, what is AM, automatic and manual, VS. I'll get the result. I can also get the proportions, like 12 divided by 18, I'll get it here. 7 divided by 14.5, I'll get this percentages, right? Last comes the Fisher's exact test, normally used when your data set is very small and the expected frequency is less than 5 in one of the cell. Okay, expected frequency, not the observed frequency. Expected frequency is less than 5 in any cell. Now, the null hypothesis for Fisher's exact test is there is no significant association between VS and AM. Here, there is a significant association between VS and AM. Attach, that is empty cars table VS AM. I'll run this, and then Fisher's test is carried out, where I'll get the p-value. So here, as the p-value is more than 0.05, we fail to reject null hypothesis and we interpret that there is no significant association between the car being vertical, that is the vertical and straight engine, with the automatic and manual transmission. All these codes are available in my book, which is available on amazon.in as well as amazon.com. This book. You can follow me on LinkedIn and Twitter. Kindly subscribe to my channel to get more videos on R. Thank you.